This tutorial is going to cover the electrical flow diagrams of the wash pump motor, the rinse pump motor, and the conveyor motor. We're going to show the components from the inside of the control box to the motors and the reed switches. To get started, we have to understand how the electrical flow is going to get to these devices. First, we're going to start out in our tutorial by connecting the main power. The main power should be connected from an electric company or certified electrician. We connect L1, 2, and 3 from either a circuit breaker or from a disconnect. Periodically, you'll have high voltage or what we call a stinger leg attached. This is a hot leg of 140 to 200 volts and should only be connected to L3. In the event that we're connecting, we should always verify with our multimeter the voltage on each leg. Each leg should represent 115 to 120 volts. A stinger leg is normally identified from an electrician or an electric company when it's installed, and it's usually wrapped with some type of odd colors or markings or tape to identify that it's different from the rest. In either event, always verify your power, and again, it should only be connected to L3. We'll cover the reason why here just shortly. When main power is on, and regardless of the dish machine is off, there are certain components within the control box that are always going to be energized. Let's take a look at those. So from our main power terminal, main power is going to be connected to the heater circuit breaker, the wash pump contactor, the rinse pump contactor, and the conveyor contactor. These will always have high voltage energized as long as the disconnect or circuit breaker to the machine is on. Also, L1 and L2 will be connected to the transformer. A transformer is designed to take high voltage and reduce it to low voltage. If a stinger leg is connected to a transformer, it brings in 140 to 200 volts of current into one leg. The transformer is only designed to reduce current to a certain amount. If higher voltage is into it, the amount of current coming out of the transformer will also be higher. This will bring your 110 control voltage that we're looking for to a higher range, possibly 130 to 150 volts. This could actually cause problem to the control voltage circuits within the dish machine. This is the reason why a stinger leg or high voltage leg should always be connected to L3. A transformer has two 3-amp fuses coming to it. Those fuses are primarily designed to protect the transformer. Once the high voltage of 208 volts and 2 legs transfers through the transformer, it now reduces power down to control voltage or 110 volt circuit. The transformer also is designed to create a neutral or a common coming out of it. Control voltage has to be completed by having a common and current connected at the same time to be able to complete a circuit. So now we see that we have power that comes to our heater circuit breaker, our wash pump contactor, rinse pump contactor, and conveyor contactor. Also goes to our transformer. It also sends control voltage to your on and off switch. These are all the components that are energized even when the dish machine is not on. Always use caution putting your hands into a control box where power is still energized. Now let's take a look at where this energy goes once we turn the machine on. Once we turn the machine on, we flip the switch. Power now comes from your on and off switch to two locations. First, it should turn on the light to let you know that the machine is on. It also sends a leg of 110 control voltage current to the power terminal switch. This is the control power terminal. The control power terminal is split into two sections. There is the upper and the lower section. Again, this is designed for safety of the machine so that the machine doesn't operate when the door is open. Once this voltage comes from the on and off switch to the upper part of the terminal, it energizes the top part of the terminal. Any devices that are now connected to the top part of the terminal will be energized. To simplify this discussion, we're only going to be focusing on the wash pump motor, the rinse pump motor, and the conveyor motor. Two sources of energy is going to come out at this point. One is going to go and energize the rinse ice cube and the wash ice cube relay contactors. It's also going to send a leg of control voltage to your door switch. While a door is open, the door switch is a normally open circuit. When the door is open, this is where the voltage stops. When we close the door, it closes the switch and allows current to flow from the door switch to the lower part of your control power terminal. This now energizes the lower part. Anything connected to the lower part of the control power terminal will now be energized. The reed switches are connected to the lower part of the control power terminal. When the door is closed, power is emitted to the lower part of the power terminal and then transferred through a black wire through the conduit down to the reed switches on the bottom of the machine. This black wire is split so that it connects to the wash reed switch and to the rinse reed switch. The reed switches are normally closed circuits. As long as the sequence bars are not engaged and the magnet is on top of the reed switches will stay open and no current can flow through it. Now let's take a look at what happens when a reed switch is activated. To do so, we enter a rack into the system. The rack activates the sequence bar for the wash side. When the sequence bar is activated, it moves the magnet from on top of the reed switch. This allows the reed switch to close, which is its normal resting position. When the reed switch closes, it sends power through the reed switch through a red wire that travels back up the conduit to the top of the control box, and it connects to the wash ice cube relay. When this red wire on the wash ice cube relay is energized, it closes the contact on the relay and allows low voltage to transfer from the ice cube relay over to the wash pump contactor. This 110 low voltage current energizes a magnet within the wash pump contactor. This magnet pulls the contactor closed. It allows high voltage to pass through the contactor and down to the wash pump motor. Let's go back up to the wash ice cube relay. There are two wires that comes out the bottom of this one, a red wire and a brown wire. The brown wire is what's going to activate the conveyor motor. When the red wire gets energized through the ice cube relay, the brown wire also gets energized at the same time. This now allows the 110 low voltage circuit to energize the conveyor contactor. This energizes a magnet that pulls the contactor closed. allows high voltage to pass through the contactor and to the conveyor motor. This allows the racks to be pulled through the machine and the wash pump motor to be cleaning the dishes. Now, as the rack is running through the dish machine, it will engage the rinse sequence bar. When the rinse sequence bar is engaged, it removes the magnet from the top of the rinse reed switch. The rinse reed switch, again a normally closed switch, falls to its normal resting position and allows voltage to pass through the switch, through a blue wire that now travels up the conduit to the top of the control box and connects to your rinse ice cube relay. When the ice cube relay is engaged, it closes its circuit and allows energy to pass through the relay through a blue wire to your rinse pump contactor. This low voltage energizes a magnet which pulls the contactor closed, allows high voltage to pass through the contactor, and activates the rinse pump motor. That's how simple the motors run. Now, let's take another look. We're going to break this down a little bit more simple. When we're looking at all this, it can be a little confusing. So let's break this down to more terminology that we can understand a little bit better. Let's take a look at the wash pump motor. Here we remove the elements that basically is not going to interfere with what we got to do to understand how the rinse pump motor is going to run. So first we're going to take a look at that our power to the reed switches is still coming from our control power terminal. When the rack enters the system, it activates the wash sequence bar. Activating means that it pushes a rod in. When a rod is pushed in, it moves the bar out of the way. It removes the magnet from the top of the reed switch and allows the reed switch to go to its normal closed position and current to pass through the switch. The reed switch has a white wire that comes out of it. There is a connection from the white wire to the red wire. The red wire is what travels up the conduit to the top of the control box and connects to the wash ice cube relay. Once this ice cube relay is energized, it closes the relay circuit, allows voltage to pass through the circuit, and energize the wash pump contactor. When the wash pump contactor gets this low voltage, a magnet within the contactor energizes and pulls the contactor closed. Once the contactor closes, it allows high voltage to pass through the contactor, activates the wash pump motor, and we start washing dishes. This wash pump motor runs at 208 volts, 3-phase. Each hot leg should read 115 to 120 volts and should max out between 8.5 and 9.5 amps on each leg. When the wash pump motor is engaged, we go back up to the wash ice cube relay. There are two wires that comes out of the wash ice cube relay, a red wire, which is activating your wash pump contactor, and a brown wire. The brown wire gets energized at the same time as the red wire does. This low voltage is transferred over to the conveyor contactor through a brown wire. This low voltage energizes a magnet, which pulls the contactor closed, allows high voltage to pass through the conveyor contactor, and it energizes the conveyor motor. Now the rack is being pulled through the machine at the same time the wash pump motor is washing the dishes. The conveyor motor runs at 208 volts, 3-phase. Each hot leg should read between 115 and 120 volts at a max of 1.5 amps. Now once the machine is running and the wash is going and conveyor is going, it's going to eventually hit the wash sequence bar. The rack will activate the rinse sequence bar. It will activate the rinse sequence bar. This works the exact same function as a wash sequence bar. When the rinse sequence bar is engaged, it removes the magnet from the top of the rinse read switch. This allows the switch to close. Current can flow through the switch. This time it's transferred to a blue wire. Blue wire travels up the conduit to the top of the control box and is connected to the top of the rinse ice cube relay. When the rinse ice cube relay is engaged, it closes the circuit, allows power to transfer through the ice cube relay to the rinse pump contactor. This low voltage energizes a magnet, which closes the contactor, allows high voltage to pass from the contactor through the contactor to the rinse pump motor. We're now rinsing our dishes. The rinse pump motor runs at 208 volts, 3-phase. Each hot leg should equal 115 to 120 volts at a max of 1.5 amps. Now let's go back up to the rinse ice cube relay. There are two blue wires that are connected to the same terminal on the bottom side of the relay. One is going to the rinse pump contactor. The second one is going over to the 6-second delay. 6-second delay is designed that when it receives voltage in, a timer mechanism inside counts down 6 seconds, and then it energizes a purple wire that activates the final rinse solenoid. The final rinse solenoid is what's bringing in your hot water, 180 plus degrees for your hot water sanitation, or for rinsing for your chemical sanitation. The 6-second delay is designed so that it does not waste energy or water waiting for the rack to reach it. Now when the rinse ice cube relay is activated, it also has a brown wire that's connected to the bottom just like the wash. The brown wires actually jump between the rinse and the wash. So no matter which ice cube relay is activated or both at the same time, the conveyor motor still operates. So again, when the brown wire is energized, it sends low voltage over to the conveyor contactor. This low voltage energizes a magnet which closes the contactor, allows high voltage to flow through the contactor, energizing the conveyor motor, and continues to pull the rack through the machine. When the sequence bars are disengaged and the magnets are back in place, this closes the circuits to the reed switches, which stops the motors from running. Again, the conveyor motor runs at 208 volts, 3-phase. Each hot leg is equal to 115 to 120 volts at a max of 1.5 amps. Here, we put the machine back together again. When we're looking at the wash motor, the rinse motor, and the conveyor motor, we look at component relationships. Component relationship is very simple as what are you expecting to happen and what causes that to happen. If your wash motor doesn't come on, then you ask yourself the simple question, what activates a wash motor? It's the wash pump contactor. What activates a wash pump contactor? It's the wash ice cube relay. What activates a wash ice cube relay is a wash reed switch. What activates the wash reed switch is the wash sequence bar. It's a process of elimination back to the source, one step at a time. Troubleshooting is that simple. What are you expecting to happen and what causes it to happen? From the problem back to the source. This is an overview on the pump, wash pump motor, the rinse pump motor, and the conveyor motor on the electrical flow.